I will point out, though, that they didn't give you the correct title of this. It is actually PFLOTRAN, the bad example, okay? And I'm going to talk a little bit about introduction. I'm going to give an introduction to PFLOTRAN. What is this code? Real brief, so you just have a background what the code is. I'll discuss our code development effort, everywhere from IDEs, refactoring, testing, debugging. Then I'll move on to our open source deployment of the code and some of the choices we've made in distributing the code in that sense. A lot of this has been covered in talks earlier today, and so in those situations I'll probably just flip through those slides a little bit quicker. So what is PFLOTRAN? It's a petascale reactive multi-phase flow and transport code. By petascale I mean it runs on the machines of the past 10 years. It's open source, LGPL licensed. It's object-oriented Fortran 2003, 2008. We use pointers to procedures, Fortran classes extensively in the code. It's founded upon some well-known and well-supported software libraries. You've heard of PETC, you've heard of HDF5, Metaspar, MetaCMake. Those are pretty much our third-party libraries that we depend upon. We make an extensive effort to minimize the number of third-party libraries upon which we rely to simplify life for our users in setting up the code and running it. And we've run on up to 262,000 cores on the old Jaguar system at Oak Ridge, and just over 3 billion degrees of freedom. In general, though, due to limitations in solver technology and scalability, we run on maybe 10,000 cores or less, and on problems composed of tens of millions of degrees of freedom. Where is PFLOTRAN being used? Well, the reason I have this slide up here is not to sell you on using PFLOTRAN, is to point out that we use it for nuclear waste disposal, which is pretty much a regulatory operation. And in those situations, people really don't want the code to change at all. They want it to stay the same for the next 20 years. We also use it for some fundamental science applications. So we have climate, we have biogeochemical modeling. At the Hanford site, we have a number of fundamental science, office of science applications. And so we kind of have these two polar opposites here. Fundamental science wants to make, we want change, we want better process models, we want advancements. The regulatory side says, no, we want to leave this thing alone. And it's a challenge with code development. Numerical methods that we use are spatial discretization. We use finite volume method. We handle structured and unstructured meshes, our grids. We're backward Euler in time. We use nonlinear, linear solvers. These are pretty much your Newton's method and your Krylov solvers or direct solvers. And then our multi-physics coupling, we couple flow and transport sequentially. Our reactive transport's global implicit. We have a number of other codes that we couple to it. One is a geomechanics capability that's built inside of PFLOTRAN, and we also couple to a geophysics code, E4D, out at PNNL. We use our motivation for high-performance computing. I'm preaching to the choir here, but our motivation for high-performance computing is because it enables us to advance our science quite a bit. And the reason I say that, this example up here in the right-hand corner is a data assimilation example. Xinguan Chen out at PNNL. She'll use ensemble common filters. She'll iterate with ensemble common filters. She'll iterate on this, and she will invert for uranium concentrations at the site. Each one of her iterations requires about 500 realizations. Each realization we apply 128 cores, so that's 64,000 cores total. She can run one iteration in about an hour and a half. If you do the math on that, that's over 7 years of compute time that she chews through in one iteration. And she can take anywhere from 7 to 10 iterations. And so right there, that demonstrates the power of high-performance computing in solving these science problems. Other aspects of our computing capability, open source collaboration. We like to have everyone in the world who wants to be involved. We invite them to be involved. It allows us to leverage a diverse community. Why do we use Fortran? This is a question that everybody asks, because this is a fairly new code. It was rewritten from scratch back in 2007. The reason for Fortran is we have a lot of old timers with a lot of know-how. We want to keep them engaged. If we wrote it in C, which is my preferred language, they would have checked out. Another reason is because with modern Fortran, there's a lot of modularity that is available with C++, classes, pointers to procedures, makes life much more easy with Fortran nowadays. And then we use a large number of existing capabilities. Okay, this is the timeline of PFLOTRAN development. And I'm going to go off on a little bit of a tangent here. Years ago, when I showed up at the University of Illinois for my master's program, I went in and talked to my advisor, and this is when I was interviewing. I said, I want to write a groundwater model. And his response to me was, the mod flows of this world have been written. Now, mod flow is the most common groundwater model that there is. It was written in the 80s. Everyone's still using it today. But his response was pretty much, listen, you're going to come here, you're going to use existing codes, and you're not going to be writing any new codes. And I kind of accepted that and came to the University of Illinois. When I came to the University of Illinois, I happened across a fellowship which took basically subsurface simulation, and I had the opportunity to apply high-performance computing to it. I looked into, my dissertation was on physics-based preconditioning for subsurface simulation, particularly reactive transport. And my point is that, there may be PhD students here or postdocs here that may have been told the same thing, that you're going to need to use an existing code, new codes aren't going to make it. Well, that's possible, but I would argue that we want people to try new efforts. We want a newer, more novel capability being developed. I was fortunate in my case that it panned out, and it's been a fun career path thus far. So I showed up at Illinois in the late 90s, came across Peter Lichtner at Los Alamos. We teamed up, got my fellowship. Our first release of the code was in 2003. In 2007, I mentioned that we were actually, as part of a SIDAC project, we had to refactor the code for adaptive mesh refinement. And at that point, we basically chose to just write it from scratch, brand new. And so we did. Since then, there have been a number of other developers involved and a large number of institutions. In 2013, we completely refactored the upper portion of the code where we handle process models. It used to be that we had one time-stepping loop. We now have a time-stepping loop is essentially an object, and we have nested objects. So we have nested time-stepping loops that, think of a linked list. You can put as many in there as you want, and you can link them in a number of different ways. And I could go into that in a side conversation if people wanted to know more. These are our developers. It's mainly men at National Laboratories. We have our one woman, Jen, I call her Goat Girl, out at Sandia National Labs. She works with me there. The rest of these individuals are mainly at National Laboratories. Peter is retired, lives in Santa Fe. He is the mastermind of PFLOTRAN. He wrote FLOTRAN, the serial version, years ago. And then Paulo here is in Edinburgh, Scotland. He's actually a private consultant who makes money using the code and consulting with it. All right, our code development. All right, I got to know this. How many people here, I want your primary IDE. How many of you use Emacs? Okay. VI? Oh, that's interesting. Kate? No Kate users. Jen uses Kate. Visual Studio. All right. You and me, that's the only ones, huh? Xcode. Okay. So Barry will trash talk Visual Studio, and I understand that there are concerns about Visual Studio, but if you go back into the late 90s, Visual Studio was one of the only good IDEs for Fortran that there were. It was compact Fortran back then. So I started using Visual Studio, got well versed in it, and I can rip out code right and left with Visual Studio. One thing I will say is that Visual Studio with Fortran 2003-2008, with the way we have it implemented in PFLOTRAN, is a little bit slow in compiling the code. And that has been an issue. But for me, ripping out code is Visual Studio. So my argument, pick the one that best suits you, fall in love with it, and use it to its greatest extent, just like Barry said earlier. Okay, benefits of IDE and refactoring. Well, this is pretty obvious. You have automated generation of dependency lists. Barry talked about how you can generate those with GNU. I've actually written Python scripts for the Linux side for our makefiles and generating the dependency lists. Bookmarks, code completion, formatting, global search and replace. I use that all the time. I don't know why anyone, Fortran 77 codes with 6 characters, why can't you just do a global search and replace and put something more verbose in there to make it more readable? But people don't do it. The integrated compiler, so you, like Barry says, you can click on the link that has the error message, takes you right to the line of code where you can fix it. Very useful. Anyone not using an IDE is kind of shortchanging themselves, spending a lot of time writing in an inefficient manner. Testing. We have unit tests. Inside the code, we have equations of state. So you can calculate density, viscosity as a function of pressure and temperature. We want to test those capabilities individually, so we use unit tests for those. Same thing for constituent relations. Saturation functions, relative permeability functions. That's all kind of jargon around subsurface simulation. But think of a function where you put a few variables in, you get a secondary variable back. We use PF unit. That is a unit testing suite put out by researchers at NASA and I think Northrop Grumman. And it's designed around Fortran and it's worked very well for us. For regression testing, basically did the solution change tests. We have written our own custom Python scripts for this. We made that choice long ago. It's worked out very well. We have a regression module in PFLOTRAN where we can sample the solution variables at the end of a simulation. You provide a block in the input file where the cells that you want to be sampled, and then we spit that data out to a file. We compare the .regression file with the gold version, and then we have a way of checking convergence based on tolerances, whether they be absolute or relative. This is just the input deck, the sections about regression. So there's a regression block, and this is a list of variables for output that you would put out to an output file, but in this case, they'll go to the regression file. This is the regression file. We sample the maximum value, the minimum value, the mean across the entire domain, and then the values at the various grid cells. Now you'll notice this is liquid pressure, this is a metaturbinite, this is a mineral, this is the rate. You'll notice that the rate here is 0. And how do you do a difference on 0? That's pretty difficult. But we can, this data here actually, we catch, I'm going to show you an example where we catch an error in the output, or in the simulation based on this. And so the maximum, min, and mean is very useful still in catching errors. I'll show that here. We also track time steps, Newton iterations, and so forth, and we catch any deviation on those. On integer values, if it changes at all, it's marked as an error. Okay, so we can launch the regression test and unit test from the make file. You can launch both using make test, and it will run them. I'm going to show an example of that if I can get it to pull up here in a second. We can also run the regression test from Python. You can launch it with the Python script with the arguments. This is our argument list for our script. It's quite complex. There's a lot of capability there. It can be recursive. You can select certain suites. You can select just chemistry, flow, transport. You can do a dry run. You can just run through them all and make sure all the linkages are running properly. Ben Andre, who used to be at Berkeley National Laboratory, wrote this capability for us. Next to version control, this is number 2 as the most impactful tool that we've had as far as developing the code. I mean, I'm here to, I witness to you that if you make changes to the code and you have a nice coverage with your regression testing suite, you can be assured that nothing has changed. There's nothing like making major changes and sitting there wondering, what did I break? That is a huge issue. This is one of our configuration files. So this is just a standard regression testing run. This is a list of all the tests to be run in this directory. These are the parallel tests. These are the default tolerances for this file. And then you can go in and you can actually change the tolerances for specific tests. So there's a lot of flexibility here. That is where this comes in very nice. Because if you go on different platforms, you've got to loosen some tolerances. This makes it so you have infinite flexibility. We have defaults in the main regression test Python script, defaults for the directory, and defaults for, and we can override those with what's for each test. Very useful. Okay, here's the output. Well, I'll run it real quick. Let's see if I can Alt-Tab out of this and not mess something up. So this is a Linux box out at Los Alamos, out at Sandia National Labs. And the regression testing is running. Hopefully you can see those dots being printed along. Each one of those is a regression test. My rule of thumb is a regression test should run in less than a second. Some of ours go for 2, 3, or 4 seconds, but I always try to get them down to less than a second. These tests will run in less than 3 minutes, so you don't have to wait forever to determine whether you've broken something. You can know it right away. So here's the output that you would have seen if I'd run both the unit test and the regression test. There are the 38 dots for the 38 unit tests. That's not a lot of unit tests. We mainly do the constitutive relations, equations of state, and the code. We could do more unit tests. We need to put more unit tests in there. And then our 179 regression tests are right here, ran in 185 seconds, and that's the output you get. So here's a little experiment. I'm going into the equation of state for water. I'm going to perturb the critical pressure of water by 10 billionths of a percent. Basically take it, add to it 10 to the negative 10 times the critical pressure. Here's the output from the regression test. You'll also notice that the unit test catches it with a failure right up there. But it's a very small difference. It's 0.4 times 10 to the negative 11. So the tests fail. We know that we broke something, so how do we get to the bottom of it? Well, we can go into the output file, the log file for the regression test. It has the name PFLOTRAN tests with the date and time that it was run. It also has a status, or the current change set for each of the repositories we're running, PETSI and PFLOTRAN. If you do a HG status, we use Mercurial. So HG status, we see that the equation of state for water was changed, so that's probably where the error took place. But we also have this other information in blue here, these commits. Gives us a lot of information if we need to go back and track down what went wrong. Here's the output from the test log for a successful test. Tells us the command that was run, how long it ran, and the diff, and it passed. And then here's the output from the failed test. And you can see here a couple of these, liquid velocity changed. It's just above the tolerance. And the metaturbinite, the minimum value for metaturbinite in the domain changed ever so slightly for the rate. And it ignores for minimum values, it ignores 0. That's it just throws that out. So with this information, actually mainly with that information right there, I know what happened. I just go do a diff on the equation of state for water, that file. Okay, we also have a build bot. This sits at Lawrence Berkeley National Laboratory. Every time there is a change to the main repository, that build bot is pinging the Bitbucket repository, downloads the code, rebuilds it all, and reports any errors. The errors are visual, but it will also send you an email letting you know that someone broke it. And it puts their name on it, which someone said that they don't want to cast any blame. I think it's good. When this shows up red like this, the person who caused it is working frantically to clear their name. They do not want to have that out there with their name associated with it right there. That's my name right there after that change earlier. Okay, now let's move on to code coverage. I use Intel. I use CodeCov. I use a lot of the Intel capability because we use Intel Fortran compilers, but I also use the GNU compilers quite a bit. It's real simple. It's so easy to do code coverage. People need to just try it and use it. You basically source the compilers, you add these 2 lines to your makefile, run your regression test suite, use profmerge to merge all the dyn files that are output from running those simulations, and then use CodeCov to generate the HTML output. This is the default name, codecoverage.html. It puts out a opening page shown right here. The overall statistics are up here, the covered files down here, everything uncovered with 0 coverage is on the right-hand side. All good information. If we look here, it has the files that are covered, functions, and blocks. It doesn't have lines like gcov does. But blocks is good enough because all the lines in the blocks would be covered or not. So you see that our coverage is about 88% for files, 67% for functions, and 51% for blocks. And that may seem bad, but I'll demonstrate that a lot of our blocks should not be hit if the code is running successfully. We have a ton of error messaging in PFLOTRAN. Why have I invested all this time in error messaging? So that people don't send me emails or call me. So they read the error message and say, oh, I did something wrong. And so, but on a successful regression test, those error messages won't pop up. We do have a version of the regression testing suite that does run those error messages, but that's a tedious effort to get all those fixed and running properly. Should do it, should work on it more. Okay, so some examples of poor coverage, good coverage, and excellent coverage. Poor coverage is dataset map.hdf5. This is on the uncovered files list, 10 functions, 503 blocks, and nothing is covered. I'll show you in a second. Material, 24 functions, 17 covered, 70% coverage, 50% of the blocks. But this is actually a fairly well covered file. I'll show you why. And then this one, there's one single code block that is not covered, and that's an error message. So here's material.f90. If you look at the entire file, it will have red, meaning nothing is covered. Bad news. We just haven't written any regression tests that use this. This is actually for capability that I never use, so I don't write them, and someone else should really write the regression test. Material.f90. These are blocks, it's hard to read, but these are blocks that would be hit if there was a mismatch in material. But we don't fail, so it isn't going to go into those blocks. We have a lot of these error messages throughout the code, through the setup portion. These are actual uncovered blocks. This is for anisotropic permeability. We really don't run with that very much. In fact, we don't care for it because it requires dispersion tensors that we don't want to support. And then that is a reference pressure that we really need to, that one needs a test. This is an uncovered subroutine in the same file. If the entire subroutine is not covered, it's red. If the portions are covered, the uncovered portions are yellow. And then here's my error message in that last one that has excellent coverage. This is basically an unrecognized keyword from the input file, but we don't have any unrecognized keywords. Not a problem. Graphical debuggers. This is a must. Peter Lichtner, the old timer that lives in Santa Fe, still uses print statements. It just kills me that he's using print statements. I'm like, Peter, just go buy a debugger. The problem is DDT doesn't come on, it's pretty much the only affordable debugger that's decent, and it doesn't come on Macs. Bummer, I see all these Apple symbols out there. That's a bummer. The other thing is I wouldn't use GDB. I started in the early 90s when I started programming in C. I used IDB. That was for HPUX debugger. And it's decent for beginners, but really there's so much capability in these GUIs that you just can't afford to not use them. I use Allinea DDT. I've used TortalView for many years in the past. I also use Visual Studio. Visual Studio's ability to debug Fortran 2003, 2008 is horrible. And their turnaround on reporting bugs is about 1 year, so I gave it up. Their debugger guys fight with their graphical user interface guys about whose fault it is that the debugger can't show symbol information. Allinea DDT, in my opinion, is the best. It's the cheapest, and it has the best capability today. Memory debugging, I use Intel Inspector. A lot of people use Valgrind, it's free. But since I have the Intel suite, I use that. I like to use two debuggers. In fact, I bought a license that has 2 seats so that I can run them side by side. So I make a change in my water equation of state. It's not matching. Why not? Then I just start up the 2 debuggers and I start marching them right along. The first thing I look at is the residual equation for both problems. If it's different, then I figure out why it's different. I have spent a few hours with 2 debuggers solving bugs that would have taken me days with 1 debugger. It's well worth it to spend the money. If you're at a national laboratory, you're charging about $200 an hour. That's probably cheap. You can pay off a debugger in no time. And student versions are cheap too. You can get it for a lot less than $600. They want you to get addicted as a student so that when you go to your job, you pay the full price. Okay, open source development. This is gonna be a little bit of fun. It seems like in the past 5 years, everyone calls their code a community code. You can't really call your code a community code. A community of users grows around a code. And the more fit codes have a larger community. So community does not imply open source, nor does open source imply a community. You have open source codes and communities grow around them. I'll contend that the successful open source codes are not designed by committee. They have a benevolent dictator who basically makes choices that address and protect the needs of the entire community while still trying to help out the little guy. So the little guy wants to make a change to the open source code. Well, the dictator is going to make sure that they don't damage what everyone else is doing, but being open source, we really want to accommodate everybody. And so every code needs that benevolent dictator. If you try to design by committee or by a consensus, a committee coming to an agreement, it's never going to happen. Your iteration on development is going to take years. You're never going to get there. So you really need that. That's just my thought on that. The other nice thing about a community is it causes the code to evolve beyond its original intention. So I'm all about subsurface simulation, but a number of my co-developers up there are into surface water flow, are into geomechanics, are into other capabilities that I never would have thought of putting in PFLOTRAN. But they came along and got interested in subsurface, and they said, hey, I want to put geomechanics in. All right, let's try it. And let's put those capabilities in. Okay, advantages of open source code. Well, it definitely encourages collaboration, development, testing. Debugging is awesome because you have a whole planet of people who are executing your code and reporting bugs. That is huge. All those people that are worried about putting their code out there for fear that there's going to crash, big deal. Someone will report that and you'll be able to fix it. Other nice thing is transparency exposes implementation details that are not published in papers. I mean, how many of you have gone to a paper, saw an equation or something how you want to implement in your code, but when you try to get the details of how to implement it, the information is just not in that paper? Yeah, a lot of you, me too. In fact, I spent a month on it back during my dissertation, only to email the author of the paper who said, oh, we just truncate the values. And so there's minimum concentrations. I was trying to figure out how, with a dispersion tensor, how he doesn't get negative concentrations when I was. Oh, we just truncate him at 0. Well, that would have been nice if he'd put it in his manual, so I would know that. So the details are there. You have to dig through the details in the code to figure it out, but the details are there. More optimal use of funding. You can pool funding across many different projects. We have a large number of projects feeding money into PFLOTRAN. Probably number of FTEs total going into PFLOTRAN is probably 3 or 4. That equates to well over $1 million a year. But it's piecemeal across a lot of different projects. Licensing fees, people are paying $60,000 for a licensing fee. That money can be put into development. And the nice thing is the little guy, the guy at the university who has very little funding, it's of infinite benefit to him or her because they can pick it up and use it without paying a fee. And hopefully, in the best situation, if the natural selection model runs its course, bad codes die, good codes survive. And bad codes really need to die. They should not be sustained for political purposes. And it happens a lot. Okay. Potential disadvantages of open source. Newbies, looky-loos. Lots of people asking lots of questions. That can chew up a lot of your time. And that's perhaps where good documentation can help out. Care must be taken to not expose unpublished research. That can be an issue. A lot of people don't put their capability out there for that very reason. I actually, if I have stuff that hasn't been published, I still push it back to our main repository because really, if anyone's really willing to dig in there and figure out what I did, they've invested the time, they can have it. They're not going to get that far ahead. One's own capability can be leveraged against oneself. That's happened to me several times with PFLOTRAN. On competing proposals, people will propose to use PFLOTRAN at an opposing laboratory, or on an opposing code base that I'm contributing to. That's stung me a couple times. So you have to be careful there. Dissension among the ranks. So you have people who fork the repository, make changes, but they never want to push them back. And that can be a little bit of an issue. Not so much for PFLOTRAN. There's probably only one fork that needs to get pushed back that has not been. And then I refer to this as disingenuous licensing, but how many people out there, they license their code as open source, but then they keep it behind a password protected repository? Then why did you make it open source? So you can release it later? Or so that is one disadvantage, is they do it for political purposes so that program managers are happy, but it really doesn't, it's not the true spirit of open source, which is getting it out there so others can contribute. Okay, so PFLOTRAN support infrastructure, we use Mercurial. I know that Git is becoming the version control, distributed version control technology of the future. I'm not really worried about it. I have a little slide on that in a bit. We support the code it's on Bitbucket. There we have the repository with Mercurial. You can download it with that command. Source tree, commit logs, you saw this earlier, pull requests, issue tracker. I'll go through some of this. We have our build bot that I discussed earlier. Our user support and developer interactions are mainly through Google Group and mailing lists. Google Groups is very good at weeding out spam. Our PFLOTRAN dev here gets 100 spam emails a day, and we've only had a few come through in the 3 or 4 years that we've been using Google Groups. Very good. And I use Google Analytics to track behavior. PFLOTRAN documentation, real quick. Currently, we have a user manual that's written in LaTeX, and it is in the open repository, in the PFLOTRAN repository. We also have design docs that are in a separate repository that is password protected, because that's where we store the tricks of the trade, is in those design documents. A lot of the way we calculate derivatives are challenging, and we don't put that out there. They are in the code, so if someone wants to go look at the code and figure it out, they're welcome to. And in all honesty, if someone would just email us and ask us how we do it, we share it. We just don't lay it out there for anyone to pick up. And then we use Bitbucket, the wiki, for a quick guide on how to set up input decks. In the future, so in July, we're toiling between Markdown and Make Docs versus restructured text and Sphinx for our future for documentation. We essentially want to merge the wiki and the user manual into a single documentation repository that's HTML or PDF or, well, HTML or PDF. The Git trend is toward Markdown and Make Docs, by far. We actually started out thinking we were going to go that direction, and then we tried both of these out, and we decided to go with Sphinx and restructured text for the following reasons. Markdown has a large number of flavors, and which one's going to rise to the top? We don't know, and we don't want to invest a whole lot of time in that. The other issue is that the way we do our quick guide with the keywords in the input file, we nest them in many different files, and we want to make them be linked. And Markdown, you cannot do that. You cannot, or Make Docs could not construct that type of an HTML linkage for us, whereas Sphinx could. And so we have chosen to go restructured text in Sphinx. We did all of this. Jen did all this. She did this in about a week's time, not full time, just probably 3 or 4 days. You just make a little prototype documentation, both, and try them out, and you see what you like. And so she did that. We're going to go that direction. And in the future, if Markdown's the path, we'll just use Pandoc to convert it over. Pandoc will nail 95% of the conversion. We'll fix the rest. So that's our plan. Some comments on Mercurial, because Git is just so great. Why are we not signing up for Git? It's like a religion, Git versus Mercurial. Mercurial tends to be more user-friendly. And really, there's nothing in Git that we've had to have up to now. When the day comes that we need Git, we'll convert over and use Git. We're not averse to using Git. We just are sticking with what we've used for the past nearly 10 years. Some functionality in Mercurial that I really like. Well, the most basic one, HG revert. Someone was talking about earlier about being able to revert back changes. Back when I was a software developer in undergrad, came my way through school, we would check out files by appending our initials to it, make our changes, check it back in, only to find out, oh, dang it, how do we go back? So we have to go back to the previous night's tarball, pull it out, and you could do it, but how nice is it to just revert back to a change set back in time? Got to do it, version control. HG bisect. You have a copy of the code that passes the regression test, another copy that doesn't, but you only found out maybe 2 months too late. Well, bisect, you can sit there and mark your good and bad one, and it will use bisection to go right through that change set that caused the error. Very useful. A little clunky or a little confusing at first, but that's a very useful tool. I've used it many times. Another nice capability I like with Mercurial is it has this HG activity extension. This is the number of commits by user from 2007 to 2014, kind of a fun statistical analysis you can do on the repository. So we're with Mercurial for the time being. All right, here's our user manual. It's in LaTeX, just a slide. Here's our Bitbucket site, where we have a brief introduction to the code. We have our installation instructions. If you go down further, there's things on code development. We have a Fortran coding standard. No one reads it, but it's there. There's a number of other things like that people should be reading, but they don't. But we like the site. Here's a keyword. This is in the quick guide for chemistry, radioactive decay reaction. We have the keywords, an explanation of the keywords, optional cards, required cards, some examples down here on how to set it up in the input file. We don't use XML. We like our own format. It's much more user-friendly. Here's commit log. You see the merges from various users. This is back in May. Jen and myself and others. A little bit of a message there. This is a nice commit. This is Jen's commit. Jen is very good about being verbose on her commits. So she's got a paragraph on what she did. Mine is usually about 8 words. So she's very good, and we know exactly what she did. And then down below it shows us all the changes that were made to the code. You're probably all familiar with this. Pull request. So when Jen first came on back in December, she was a new developer, and she did not have push privileges to the main repository. And so she would submit pull requests. We would review them. I said here, I hate to do this to you, but I want to suggest the following modifications. She'd go back and make the modification. Then eventually we accept the merge, or the pull request. We merge it. One thing that's nice is even among developers now that have push privileges is we use pull requests to do code review on each other. So you create the pull request, then you add people's names to review it. We all kind of converse about the changes, decide whether to continue with it or whether or not. HG blame. This is also a fun one where it lists basically every person who's changed a line of code. The last time that line of code was changed, by whom and what date. That's useful for trying to figure out who in the heck wrote what block of code that's causing problems. I wish it had a history, though. I wish we would have you could click on that and see all the changes back in time. But it'd be hard to do that with a line number. User support, I mentioned Google Groups. Here's our mailing list. This is our Bitbucket. This is the this is the Google Analytics map of the hits on the Bitbucket site in 2015. Most of the users are at national laboratories in the United States. There's a few at universities, major users at universities. This is a private consulting firm, Amphos 21, out of Barcelona. They have a GUI that's wrapped around PFLOTRAN, and they also support it heavily for nuclear waste disposal in Europe. And then my buddy Paulo up here in Edinburgh, Scotland. There's a number of other people. I have no idea who these people are. They may have an email address that I converse with, but I probably don't know their name. I don't know who they are. But we have a good time. What's most rewarding about PFLOTRAN is when you're at AGU, American Geophysical Unit's major conference in December. Just think of your major conference. And you're walking around and someone you don't even know walks up and says, your code's so awesome and I'm able to do this scientific problem, and they just praise it up and down. That's, I mean, I like a paycheck, but that right there is far better than a pat on the back from a manager. Knowing that you developed something that someone else used for good. Oh, that's such a payoff. Okay, testing. Jen is in the process of developing a QA testing suite, like a regression suite. We have a bunch of analytical solutions in 1D, 2D, and 3D. She's writing it in Python. It's going to run very similar to the other one. It's going to use Python. And we're in the process of QAing the code, and so we're in the process of developing that testing suite. This is a verification testing, so analytical solutions, they're very simple problems. You can run them real fast. The more complex coupled physics problems, you really can't develop an analytical solution for that, so we verify our code against other codes. In this case, this is a WIP test, Waste Isolation Pilot Plant. That's the only operating nuclear waste repository in the United States, in southeastern New Mexico, Carlsbad. They have a number of codes, Bragflow and Nuts, and Nuts is really nuts. It's a crazy code. We have to verify against their existing code to prove to the regulators that we can match the old solution before we move on to something better. And so this is just a result from that. We're comparing against Bragflow and Tough2. Tough2 is a code out of Lawrence Berkeley National Laboratory for Subsurface. Probably, as far as closed source codes go, the most popular code in the world for subsurface simulation.
So I wondered how do you think the importance of commit history? So if there is someone fork your job and they modified a lot of code in your original code, and they don't want to merge their code back to your code. And the other thing is, if they delete all your commit history, do you think it's proper or not? They still keep your like MIT license in their project, but they delete all your commit history.
Well, they can do whatever they want, right? I mean, they're free to do what they want. They probably aren't going to get their capability merged back into the main trunk.
And the other thing is, in early your slides talk about the regression test. So I wondered, how do you make sure the correct answer you used in regression test is really correct?
Excellent question. So you noticed in my slide there for the regression test, I said did not change test. So regression tests aren't necessarily, they're not concerned about whether the answer is correct or not. It'd be nice if the answer is correct. But really what we're concerned about is, did it change? It's the QA tests that are concerned with whether the answer is correct or not. I will point out that most of the QA tests in 1D are very small. In fact, even the 2D and 3D ones, they're very small, they run very fast, and we just use them as a regression test too. In that case, they serve two purposes. So with regression tests, we're not concerned about reality. We're concerned about whether it changed. Let me add on to that. We do have, it's one of those capabilities where you could probably take out a gun and shoot yourself in the toe if you're not careful. There is, with the regression test capability, you can go in and you can tell it to overwrite all the gold files, update them. But you have to almost sign your signature. I mean, there's so many commands you have to put in that you know you're doing something you shouldn't be doing when you do that. There are cases where we've had to do that, but the best thing to do is to go through test by test and see why it changed. Makes sense. All right, let's update the gold file. One thing that I do, and I did this a couple months ago, the regression tests were taking a long time. They were taking probably 5 minutes to run. I wanted to get them faster. And so you either remove redundant regression tests or you speed them up. But if you speed them up, they don't run as far in time. Did they really test all the capability? Because there's, with geochemistry, there's minerals that precipitate and dissolve. Sometimes they don't precipitate in a latent time. So I'm really testing all the capability. And so you do a code coverage. You start thinning out, I call it thinning out your regression tests, either removing them or shortening them. And then you go back and look at your code coverage. And you just have to look at the statistics there and find the files that changed, and then you go looking, you just have to compare it side by side to see what you have missed by reducing the number of tests. It sounds like a lot of work, but it probably took me a couple hours, and a couple hours is it's not that bad.
So I suppose sometimes you make changes where you want the result to change to like make your code more correct than it was before, and then you have to go and update all your tests that are now failing. And I'm just wondering if you have some kind of procedure for that, because it's easy to sort of get out of sync with your tests and think that, oh, I'll update them later, and then no one knows what's right anymore.
Well, when that happens, what I do is I update the tests. I just change the gold file, and then we send an email to the user list stating that we changed the way that this, usually what it is, there's averaging schemes for variables in the interfaces between grid cells. And harmonic mean versus arithmetic mean versus geometric mean, that's where it happens a lot. And we'll just warn the users that we've made that change. We don't really have a release model at this point in time. We're in PFLOTRAN 2.0, but when we do get to a release model, we would change the number. We would increment it so that people know they're using a different version of the code. But we haven't really implemented that up to this point in time.
In your group, how do you manage to properly acknowledge the contribution to the code? So the number of commits doesn't necessarily mean the major contribution to the code. And more specifically, should it be a mixture of commits and the comments in the code and the documentation? I mean, what are your thoughts about that?
So you're asking, where do people get the credit for their contributions to the code?
Yeah, and how? So how do you manage that, basically?
How do we manage that? We're kind to each other? I don't know. There's really no issue with this code. There's really no issue with, I think, with people trying to not getting credit for what they've done. We do track. All right. So the commit message would have it in it. We have a header on all of our subroutines where the person who developed that subroutine has their name there. Years ago, people wanted to remove that, but I kind of fought back against that because it really does, in the code, you can see who developed it. And then mainly, people kind of own different portions of the code and their name's all over it, and they publish papers on it, and that's how you get your, I mean, if you're going into open source development so that your name, you can have the glory for what you've developed, you're probably going into it for the wrong reason. So I guess we don't have a model for that. But I haven't heard any developers complain, per se. I think we're pretty good about, we got some great people. It's amazing how in a 5-minute phone interview, you know if someone's got it or not. And you want to hire them, bring them in, and they're good. That answer your question?
No, I was just wondering, I recently saw a talk by the YT community, YT Astrophysical Visualization community. So there is a community YT. They develop the visualization for astrophysical codes. So they were talking about this issue, that how that it's very subtle, because so the head developer, he gave a talk and then he got some complaint that the proper acknowledgement was not there. So, and then he wrote a separate article that this is a very subtle issue, and we still don't have like a good model for that.
Okay. So we do, like in the manual, people who do, like Jen's name's not on the current manual, her name will be all over the next manual. And we do add people's names to the manual. Haven't really crossed that issue yet.
So you were talking about graphical debuggers earlier, and I've personally really only used Valgrind because that's a free one. I was just wondering what made your favorite one your favorite?
Well, I for years I used Visual Studio, and before I dabbled in before we went to 2003, Fortran 2003, 2008, and approximately 2012 to 13, Visual Studio was fabulous. And then Visual Studio, basically if you open the objects in Visual Studio, it looks like garbage. If you open a Fortran class, it can look like garbage. It's just undefined variables. And so I used TotalView in the past. TotalView is fine, but it's kind of clunky and it's really expensive. It's several $1,000s. And so I looked into DDT, downloaded the demo copy, and within 15 minutes of use, DDT has it. I knew it was what I wanted. And there's so much capability I don't even use in DDT. And for the price, it's I want to say $500. It's not. That's compared to the money we shell out for just development, that's just a drop in the bucket. So prior experience and just the wealth of information that's available with DDT, that's why. It also, it runs in parallel, it runs serial. I have PFLOTRAN coupled to this geophysics code. I can run the whole, so there are cores that are solely geophysics and they're all kind of dancing with each other, right? And I can separate out the cores and I know where things are going wrong and I can pinpoint it. Whereas the guy I collaborate with on that geophysics code, he hasn't used DDT much, and so he uses print statements. And so I'm able to get to the bottom of it real quick.